All right, welcome everyone. So again, if you go to this link posted in the chat window, it'll guide you to this GitHub repository. You can scroll down and again, just this bottom row, we're going to work on the latest binder. So we'll click this link here, which I already have. So if you have not clicked this, please do. And if for whatever reason it doesn't work out, I will go through all of this step by step, and this will be recorded. And I also have an annotated version of all of my files as well. Okay, so after you click this Launch Binder button, you should see something that looks like this. It's RStudio, and we have all of our data already loaded in here. So just like last time, there's two different kinds of files that we'll use. We'll use this R script. I'm going to open this. I'm going to get rid of this untitled file. And also let me know if this text is too small, too big, etc. I'll also open this R markdown file. So these are two completely fine ways of coding in R. The markdown file is a little more polished. You can run code to create this into a PDF or an HTML file, and it looks all pretty. And it's also a nice way of separating annotations from code. So all code is denoted by these blocks. And then this does not get run by R. It's just annotation. So everything I'll go through today is right here. But for going through the code, I'll just reference this R script, which is a little less wordy and is more focused on the actual commands we'll run, and then I'll just describe those commands. So this is the second session covering Tidyverse. We'll show you how to use some new functions, but we'll also use some of the old functions we covered last time just for extra practice. And if you missed the previous session, that shouldn't be a huge problem. But for instance, being in the previous session familiarized you with some of the data sets that we'll be working with, which I won't describe in too much detail. Lastly, I encourage you to copy and paste this URL into your browser to look at this cheat sheet, which I've already done. Again, I highly recommend cheat sheets. It's just organized knowledge, helps memorization, and it also allows you to find which commands you might need to use faster. Okay, so carrying on from last time, let's quickly reload and clean the data sets that were basically the end product of last week's lecture. So I'm going to load in the mask data using all of these columns here, all of these rows here, where basically, we're piping the mask use wide data into a series of commands to get a long data set. So I'm just going to highlight these and run them. And I've accidentally highlighted, this stuff that's been commented out, but that shouldn't matter. Okay, that didn't work. It did not work because I did not load Tidyverse. So this should always be at the top of your files. You should have library, and then in parentheses, Tidyverse. So this will load all of the packages that are included in Tidyverse. And again, Tidyverse is like this mini language within R that has its own set of commands that the fields of bioinformatics and data science are converging on in terms of using it for best practices, in terms of writing readable code that efficiently cleans and analyzes your data. Okay, so I'm going to run these two commands, and this is mask usage data collected from the New York Times, and it's the data comes from the New York Times in wide format, which looks like this. And then last time we converted our data set from wide format to long format, which looks like this. So basically, all of the information in these columns were collapsed into 2 columns where we have a categorical variable, mask use response, that can take on one of 5 values, and then these are the proportions. So for this county, represented by some number, these are the proportion of people that never wore a mask, etc. Okay, so that's what these data look like, and we've loaded them and cleaned them, and let's keep the mask use data in both wide format and long format for today. We also worked with case count data, and let's load that back in. This will actually go directly to the GitHub repository. So I'm going to highlight this and run it. But as I mentioned last time, these data are huge because it's basically the cumulative case counts for every county since January. So many, many thousands of lines, almost 500,000 lines. And I simplified it by only looking at the most recent date. So I'm going to make a new tibble called cases latest and take this cases data, which is too large, and only select rows where the date was August 3rd. That was the latest date when I made these data. But actually, let's update this. Let's get the most latest date because we've downloaded this from New York Times and they update this every day. So how do we do that? So this is a little off script, but I always just like typing head cases. So I'm in the console down here now, just to get an idea of what the columns look like. So let's take this date column and let's sort the values such that the largest one is on top because the largest date value corresponds to the latest date. So we can do that using Tidyverse commands super simply. So let's take our cases data, and we're not going to store this into any variable. Let's just pipe that into select. So let's select the date column. And then what do we want? We want the latest one. Let's pipe that into the arrange function. By default, arrange sorts from low values to high values, but we want, let's do the reverse. Let's do it in descending order and give it the date column. So if we run this code, you can see it looks like the most recent date is August 17th, which makes sense because it's being updated continuously. But again, this is just to show you, if it weren't updated continuously, you can use a few Tidyverse commands to quickly probe what the latest date is. So I am going to change August 3rd to August 17th. And then I'm going to highlight all of this code here and press run. And this should give us a cleaned data set called cases latest, just to visualize it. And as you can see, here's each county. We have cases and deaths. There's no date column. I got rid of it because the dates are all the same for each of these data. So it's kind of not necessary. Okay, so these data on mask usage and case counts are on the county level. And so there are many counties per state. And these counties vary considerably in size. Some of them are only 100 people, and some of them are 1 million people. So if we wanted to do analyses that took this variability in size in account, we would need additional information. We can't just have case counts and mask usage. We also need population size by county. And this also allows us to, so if we look at the cases latest data, so these are the cumulative number of cases that happened in Autauga up until August 17th. But we might want to know what's the total fraction of people in this county that have been infected by coronavirus. So we need, a denominator. We need the population size for this particular county. So we can get this data. It's publicly available. I got it from census.gov and I downloaded some table. Actually, I downloaded an Excel file and I had Excel export that in a comma separated format file. And it's a little messy. And we'll clean this file up today to illustrate various tidyverse commands and combine these data on population size with the case counts and mask usage. I think a .xz file is just some compressed version of a file. I will not go into the details, but all you really need to know is that read Delim recognizes this extension and automatically uncompresses the file and reads it in. So I'm going to highlight this code, and I'm going to store the output of read Delim into a new variable called population sizes. It's not just any variable, it's a tibble, which again, a tibble is it's basically just a data table that is frequently used in this tidyverse paradigm. Okay, so let's click this new population sizes data just to get a view of it. So, there's a lot of lines. There's like 3,000 lines. So actually, I'm going to go back to this R script. And, one way to double check that your data look like you expect them to is to go through each row, which would be super tedious for large files. So when I'm dealing with large files, I typically try to probe various corners of these data using some commands. So let's look at the top of the file using the head command. Okay, so here's the top of the file. You can see it's got some column names. So this is annoying. The first row is the population size for the entire United States. So I downloaded a data table saying it had population size by county, which it does, but then they just threw in the entire United States in the first row. So we're gonna have to remove that. We can also look at the number of rows in this tibble. So let's run this command. It's about 3,000. And if you Google the number of counties in the United States, it's around this number. It's slightly less. Okay, so that's promising. We can also look at this column entitled, actually, let me make this. So there are more columns here that are not shown because so let me type this head command again. And now it'll show more columns because I have more space in my RStudio window. There's this column called 2019. These are the population size estimates for 2019. Let's see if there's missing data in this column. So we'll eventually use these data because it's the most recent estimates. And this function here basically says, take the column 2019 for the population size tibble and give it to the function isNA. So this basically counts the number of missing values in this column. But if I precede that by an exclamation point, it reverses that in the sense that it basically counts the amount of the number of elements that don't have missing data. So if we run this command, you can see most of our columns don't have missing data. If you remove this exclamation point and run this command again, you can see 6. Okay, so we have 6 rows in these data where population sizes are missing for 2019. Let's look at the bottom of this file. Okay, this is bad. It looks like some notes were left in. I mean, this is bad if we want to import a data table into R where each column has the same piece of information. So R loaded in this data, and in the first column, there were some notes, and now there's a bunch of missing values. So these are probably where the missing values came from when we typed this command up here. So again, if you're using other people's data, a lot of times you get these little unexpected surprises, and it's good to use these commands to make sure your data are what they look like. And actually, if I look at this, so again, if I click pop sizes over here and I view these data, if I go all the way down to the bottom, you can see, one second. If I go all the way down to the bottom, okay, again, this is why it's bad to work with large data sets or to view them, to view large data sets. If you scroll all the way down to the bottom, you can see around row 3143, it looks like the data end, and then the notes start here. So all of this is useful information. So let's start cleaning these data to get them in a format where we can analyze them using all of these fancy Tidyverse functions. So first, let's remove that first row that has the population size estimates for all of the US. We don't want that. And let's remove the last few rows that have those notes. We'll do that using the slice function. So slice basically allows you to select particular rows in your data. If I go to our cheat sheet over here, you can see that there are a variety of ways to select rows, a subset of them, and here's the slice function. So before we used filter, which selected rows based on whether or not values in a column met some criteria. But here, the slice function is a little different. It selects rows based on their numerical index. Cool, just checking the chat window. Looks like Tim's got that under control. Okay, so let's run this command and press enter. And let's do tons of sanity checks along the way. Let's click the population size data and look at it. Okay, you can see the United States row was removed. And let's just assume the bottom rows were also removed, all of those missing values. Okay, so one other annoying thing about these data, sorry, let me just click them again, is these, so geographic area, this column actually has two pieces of information in it. It has county and state. And if we wanted to query those pieces of information separately from one another, it's a little more difficult if all of that information is combined into a single element in this column. So what we can do is we can actually make two columns. One is called county, another is called state, that contain these pieces of information separately. So let's do that using the function called separate, which is appropriately named. So what we're going to do is we're going to take our population size data and we're going to overwrite it. We're assigning the old data set that has been fed to this new separate function. So what separate's going to do is it's going to take all of the data in the column called geographic area, and it's going to separate it into two new columns. One's called county, one's called state, and it's going to know how to separate information in this column based on what we give the sep argument. So we're telling it separate it by comma space. Because if I go back to our pop size data sets, you can see it's county, comma, space, state. So if we highlight this and run, and again, just clicking our pop size data to look at it in the viewer, boom. We have a new column called county, a new column called state, and our data were separated. I use commands like this all the time. And just so you know, there is another function that's very similar to separate. I'm going to go to the cheat sheet over here. You don't need to follow me. So what did we do? So under this section of reshaping data, we used this separate function where we took one column and made it into multiple columns. There's also another function called, unite, which takes multiple columns and compresses that into a single column. I'll not demonstrate that function today, but just know that you can go in both directions. Okay, so another annoying thing about these data, and I don't know how this happened when I exported it from Excel, but all of these county names are preceded by a period. Let's get rid of that. Also, all of the counties are they're followed by space county. We don't need that. I mean, we know that this is a county because it's in the column labeled county. So we don't need all of these county words in this column. So we can do that using the mutate function. So mutate is a function that adds new columns to our data, but it can also be used to modify existing columns. And it modifies existing columns if we just specify the same name of a column that already exists. So, county already exists in our data, and I'm saying mutate the county column such that it equals the following values. So there's actually another function here called strremove, which removes strings, so it's named appropriately, and you give the strremove function some data. So here we're giving it all of the data in the county column. You also give it a pattern. So I'm just going to add some spaces here. So here we're saying identify all of the dots in this data we're giving you and remove them. That's what this is doing. So then after we remove that, we'll pipe that to a second mutate function where we basically do the exact same thing, except we say remove this extra county label at the end. So I'm going to highlight this. And again, because we're using the assignment operator here, we're going to overwrite our existing data. You don't need to do that. We can make a new data called pop sizes too, but I mean, no point really, in my opinion, but that's completely up to you. So let's run this. And I'm going to click pop sizes again just to view it. And amazing, beautiful. Look at this clean data. No unnecessary dots, no unnecessary county names. And if we look back at this pop sizes data set again, sorry if I toggle between windows really quickly, I'll try to warn you before I do it so as to not make anyone sick. We have tons of estimates of population size. Let's only take the most recent one, 2019. Okay, gonna go back to the R script. So we'll use the select function and we're gonna select from our pop sizes data set. Let's select the county column, the state column, and only the column that corresponds to 2019 for population sizes. I'm gonna highlight this and press run. And again, just look at my data. Beautiful, worked as I expected. The more experienced I get, the less I check every single step. But I just want to show you guys each step how the file gets modified. Okay, so these data are pretty clean. This is optional. I'm not going to do this, but we've cleaned these data in a bunch of different separate steps. If I wanted to share these data with a collaborator, I would do two things. I'd send them the raw file I got. So, I'm going to scroll back up here. I would send them this original file, unmodified, that I downloaded from the internet. And I would then send them this, which is a chunk of code. That's exactly what we've just done, where all of our commands are repeated back to back. So first we read in the file, we pipe the output of that to the slice function. So these commands are executed in a series. So I'd give them the raw file, I would give them this chunk of code, and I would say, that's all I've done. And the thing that's beautiful about Tidyverse is this is self-annotating. I don't need to tell my friend, oh, in the Excel file, I renamed this column, I switched these around a little bit. Everything I've done is exactly in this chunk of code. And so this is kind of the basis of reproducible science and kind of getting everyone on the same page. So if we were to run this code, we'd basically regenerate our this pop sizes data set right here. Okay, let me get back to my notes. Okay, so now that these data are a little clean, we can take a quick look at this pop sizes data set using the summary function. I actually don't think this is a Tidyverse function. I still like it. And I'd just like to note this is different from the summarize function, which we will learn below. So let's just run this command here. Again, it's a nice way to just briefly look at your data. So it's analyzing each column, county, state, and the population size one, and it's immediately showing us the range of county sizes. You know, some are 86, others are, what is that? That's 10 million, that's probably New York. So, you know, if we wanted to get the average behavior, the average mask wearing behavior in a particular state, we can't just, you know, average across the counties. We have to take these population sizes into account because some counties are tiny and some counties are huge, such that on average, you know, these large counties are more representative of the state than the small counties. Anyways, that's an analysis we'll do very shortly. So we have 3 pieces of data now. From last time, we have case counts and mask use by county, and we've just loaded in and cleaned a 3rd data set on the population size estimates for each county. So let's use the join command to start combining these data together into one table. And please see the previous workshop about how these join commands work. So what I'm going to do is I'm going to join the cases latest data and the cases pop size data. Sorry, I'm going to join the cases data and the population size data. But I have to tell inner join how to unite these 2 data sets. I'm going to say use the information in the county column and the information in the state column. So basically, let me open up these 2 files. I'm telling this join function, for this county, Autauga, Alabama, add the population data. And the way you're going to find how to add the data is you're going to go to the population size data, you're going to find the value in the county column and add that to this data here. So that's what's happening here. I'm saying use the county column. But what looks a little strange is I'm saying why is lowercase county equal uppercase county? Well, that's because in the cases latest data, which I'll click, the county data are labeled with a lowercase, and in the population size data, it's labeled with an uppercase. So these columns are named differently, but here I'm telling the join function, even though they're named differently, the information is actually the same, and you can use them to combine the data. Another approach would be is if I renamed these columns above, such that I only give it the same count, the same name in the 2 data sets. So let's join by county and comma by state. The reason we want to do both is because I made this mistake in making this workshop. There are some counties that are represented in multiple states. For instance, there are multiple Baldwins. There's one in Alabama and there's one in Georgia. And so when you only tell inner join to join these data by county, it creates some nonsense because of these matches, these ties. And so we're going to break these matches by also separating by state. Okay, I'm going to highlight this code. And just as a brief review, I could also write my code like this, such that everything is represented on the same line. But a lot of people like, you know, kind of separating things out on multiple lines. In fact, we could do this. To me, this is the most pretty. Because then, you know, we don't have to like scroll to read things, and it's very clear that this is the first argument, second argument, third argument. Okay, let's highlight this and run it. And I'm going to click the data here just to see what they look like. And as you can see, we now have county, cases, deaths, population size. Beautiful. I'm going to go back to the R script. Okay, then, so we have this new tibble called cases pop size. Let's take that and again add on the mask use data and make a new tibble that has a very long name. I apologize, but it's informative. It's the case counts, the population size, and the mask usage. So let's again use the inner join function, and we're going to take this tibble that we just made, and we're going to join it with the mask use wide data. Let me quickly explain what's happening here. But first, let me go back to the mask use data. So again, we had two versions of the mask data. We had it in its original wide format, and we also had it in its long format. So these data are a little complicated. And so what I'm going to do is, when I'm combining the mask use data with these other case counts and population sizes, let's only take this column here always. We don't really need these other columns because all of these values sum to 1. So that if there's a county where people are not always wearing a mask, it's because these values are higher. So if we want to know if people in general are always wearing a mask or not, I mean, we can let's just use this column. So that's what's happening here. I'm taking the mask use wide data set, and I'm selecting only the county number and the data under the always column. So I'm not giving it the whole mask use wide data set. I'm just giving it a subset of that. We can see that because if you actually highlight just this all the way to the end, I believe, yep, and you press run, it'll run just the chunk of code that's highlighted. And as you can see, it corresponds to this simplified data here that only has 2 columns. An alternative would be that we make another data, mask use wide simple, that just has this information, and we, give that data table here. So this is a little complicated. It's a select function that's nested within an inner join function, so it's more compact. It might be more difficult to read, but how you do it is a preference. Anyways, I'm going to combine the cases and the population size with this mask use data, and I'm saying take the data in the FIPS column. So if I go to, what is it, cases pop size. So this is the numerical representation of a county that corresponds to the mask use data. So on the New York Times GitHub repository, their mask use data are not labeled by county. They use this number instead. So we have to join these data sets by these county numbers instead of the county names. Okay, let's highlight this and run it. And again, I'm just gonna clean up a little bit here and then click this data just to view it. Beautiful. For each county, we have cases, deaths, population size, and the fraction of people that are always wearing a mask if they're within 6 feet of another person. That was the questionnaire that the New York Times distributed. So now that we've combined these data, let's clean them up a little bit more by renaming 2 columns. Let's make a new column called population size that takes on the values in the column 2019, because by itself 2019 is not as informative as population size. We know that that's referring to population size. Likewise, there's that column that's entitled always. Let's change that to always masked instead, which we'll do using this. So we rename 2 columns in the same line because we separate them by a comma. Let's run this. And that's going to replace those 2 columns with these columns that have new names. Okay, so let's very superficially visualize these data. Next time, Tim will teach you how to use ggplot, which is way more powerful for visualizing data. Today, we'll use some basic functions in R, like plot, just to get a super brief idea of what the data look like. And let's keep all of our analyses today let's keep them as descriptive observations. Let's try not to make any conclusions or conclude that any trends exist, and let's leave all of that up to the public health officials that do more complicated analyses, which you can see are required for these data. Okay, so let's make a new column called Frac Pause. So we're going to use the mutate function to make a new column that takes all of the data in the cases column and divides it by this new information we have, the data in the population size column. So this is basically the proportion of people in each county that have tested positive. And before we even look at these numbers, I'd just like to note that these numbers may not be accurate. More and more data are accumulating that the number of people who are asymptomatic and might never get tested is huge. So these numbers could be off by up to an order of magnitude. But let's just assume they're accurate for today. A bad assumption, but we're going to assume it. So these analyses here will make a new column called Frac Pause. And instead of viewing it, let me just type the head command instead. So now we have this new column. So it basically took the cases data and divided it by the population size data for each county. So 1,000 something divided by 50,000 something is 2%. Okay, so one question we might ask is, do counties with large population sizes have a higher proportion of case counts? Naturally, we might expect larger counties to have more cases because there are more people there. But when you divide by the population size, is the fraction of people who have been infected, are those larger? So we can look at this by using the plot function. This is going to be a very simple scatter plot. On the x-axis will be population size. On the y-axis will be the fraction of people that tested positive. And this is going to be by county. And I'm going to log the x-axis because county population sizes are so variable that if we look at the log, it's a little more easy to visualize. And then this is just me labeling the axes. So let's run this command, and it should spit out a plot down here. So this looks interesting. It almost looks like a snail, where here's the shell. But I mean, if you like squint, it almost looks like the data are trending such that those counties that have larger population sizes also have, a larger fraction of people have been infected. One analysis I would like to do is to do a correlation on these data to look at any trends. But what's a problem here is as you go along the x-axis, the amount of variability in the y-axis changes. And that's a problem that violates very basic assumptions of correlation and regression analyses. What you could do is you could look at only a tiny subset of these data where it looks like the variability is the same. But if you actually do that, there's still a significant amount of variability that violates these analyses. So again, this is called heteroscedasticity, where the variance changes along one of the variables, and it violates these simple analyses. There are more complicated ones you could do that take this into account, but that's beyond the scope for today. But to illustrate more tidyverse functions or how to use them, one thing we might ask is, wow, look at these counties that have a high fraction of case counts. In some of these, it looks like almost 15% of people have been tested positive. So what are these outliers? We can easily query them using the following tidyverse commands. So I'm going to take our tibble, cases pop size best, and I'm going to pipe it to this filter function, which is going to select rows based on a criteria. Frac pause is greater than 0.08. I selected that by just eyeballing this here. So 0.08 is right here. So we're basically going to be finding which counties correspond to these points up here. And let's arrange this in descending order, where the ones that have the highest fraction of infections are on top. Let's run this code. As you can see, okay, it looks like Trousdale, Tennessee has a huge number of cases relative to its population size. Over 1,000 cases, and it has a population size of 11,000. No finger pointing or anything, but I will just highlight this element here. And I'm not going to say anything more. It's a small county. I mean, and also, because it's a small county, there might be a lot of statistical variability. So any sort of causal inference, is difficult and needs to take into account that, some of these small counties, sorry, so I actually did finger point. I showed that this county has a low proportion that are always wearing masks. But if you look at the counties where people are wearing masks the most, it's also small counties. And that's just because, small counties have the most variability. So that was wrong of me to finger point. I mean, there might be a causal relationship between this always masked and the fraction of positive infections, but that analysis requires a little more statistical rigor. Okay, so with the remaining 15 minutes, I'm going to go over 2 new functions in Tidyverse that are extremely powerful. I love them. They're probably my favorite functions in Tidyverse, and I use them together very frequently. They're group by and summarize. And let's just show you how these work with some examples. So let's go back to the mask use wide data. And this example will also illustrate one of the benefits of converting between long format and wide format. So here's our mask use data. What if we wanted the mean values of all of these columns? One way to do that would be brute force. We type mean and give mean each of these values. Sorry, for this mask use wide data set, take the column rarely and calculate the mean. So this is kind of a less elegant brute force method. And if we run this code, you can see it spits out a bunch of values, separated by our commands. Not super pretty. Another way would be to use this summary function. Again, this is different from the Tidyverse summarize function, which I'll cover in one moment. But it's still useful. We could use the summary function, and let's run this. So we still get some information here. It summarizes each of the columns and reports the mean values along with some of the other quartiles. But these data aren't pretty. Like if we wanted to plot these data or do additional analyses, on the means, for instance, it's kind of awkward. It has like colons in it, etc. A third way to get the mean value for each of these mask wearing categories is we can use our mask use long data. So let me just briefly open that up again. So what we're going to do is, sorry, I'm toggling back and forth a lot. I'll go back to this R script. So what we're going to do is we're going to take our mask use long data. So we've converted from wide format to long format. Please see the previous workshop for how to do that. And we're going to group by the data in the mask use response column. So I'm going to, this column here. So basically, Tidyverse is now taking this big data table and it's forming groups. It's going to form a number of groups corresponding to how many values we have in this column. So never, rarely, sometimes, frequently, always. So for each county, we have 5 different responses. So now in memory, R is grouping this data into 5 different subsets. And then we're going to pipe this grouping information to the summarize function. Again, different from summary. And we're going to tell the summarize function, take the mean under the mask use proportion column. So again, I'm going to go back to the data. So for each of these groupings, it's going to calculate the mean under this column. So let's run this code and see what happens. And as you can see, we get this nice, beautiful tibble. So summarize outputs a tibble. And for each frequency category, so this is averaging across all counties, this is the average number of times people are always wearing a mask. This is the average number of times people are frequently wearing a mask, etc. And so we can, this is column 2. We can easily reference this column for downstream analyses and plotting. And so I like understanding how code works by breaking it. So you don't have to do this, but let's take this line here and comment it out. So any commented out lines do not get run by R, and let's run the same code. Now it only reports a single mean, and that mean is the average for this entire mask use proportion column. Again, because I eliminated this group by function, now summarize isn't going to make any groupings. It's just going to take all of the data and it's going to calculate the mean for this column. Okay, so let's change back to our combined data. So that was the mask use data by itself, just to illustrate how converting between long and wide format can enable the use of this group by function, which is super powerful. So let's go back to our combined data that have case counts, population sizes, and mask data. And let's do a state level analysis. All of these data are at the county level, but we can super easily do an analysis by state by simply saying, take these data and make a bunch of different subsets, group the data by state, and then give that to the mask. Oh, cool. And then give that to the summarize function. And here we're going to calculate the mean of the always masked column. So what this is doing is this is basically, it'll calculate the mean of always masked by for each state. And we're going to store that data in a new column. And then let's arrange it by this new column. So again, what this is going to do is we're going to get the average number of times people are always wearing a mask by state. And let's run this code. And as you can see, we're not storing this data. It's just going to print it to the command line. And so here, for Delaware, the number of times people are always wearing a mask, this is averaged across counties, is 0.8. So again, let me just repeat that. If we take the average across counties, people are always wearing a mask 0.8, 80% of the time. So there's a problem with this analysis. And that's because we're averaging across counties, but I mean, if we go back to, let's see, if we go to, so here's our combined data here. So for Alabama, it's taking the average values of this column for Alabama, averaging across the counties. But as you can see, these counties vary a ton in size. And so when we're calculating the average, if we just say mean, it's going to treat these counties equally. But let's say we don't want to treat the counties equally. We want to weight each of them by population size. This county has a lot, 10 times more individuals than this county. So if we wanted to calculate on average, how frequently are people wearing masks, we should give more weight to this county because it represents Alabama more in some sense than this county does, which is smaller. So let's calculate the weighted mean by using these population size estimates to weight them. So that is done right here. And after I explain this command, we'll stop. I'll quickly summarize for today and stop. So let's take our, let me scroll back up. So this code here is exactly the same as this code up here, except for what we do in the summarize function. So what we're going to do is summarize is going to make a new table with a column called weighted mean masked. And what that is going to do is it's going to take the data in the always masked column and multiply it by the data in the population size column. So, and it's going to add all of those up. So let me briefly explain that using the data table. So it's going to take this value and multiply it by this one. That's what's happening here. And then it's going to add all of those values up. But it's going to do this by state because we have this group by state preceding this summarize function. And then we're going to take those values and we're going to divide by the total population size for the state. If that didn't make sense, let's look at this little figure I made. If it does make sense, you can zone out and then I'll summarize the workshop in a moment. But let's go to this figure here. So the reason I like this example is because it illustrates this concept in R, which is how it does math on vectors or lists of variables that contain a list of elements. And it does math in an element-wise fashion. So when we said we want always masked multiplied by population size, I'm going to go back to the code really quick. So that's what's happening here. What it's doing is, under the hood, this is actually creating a new vector in memory. This one here, which is basically a product of these two vectors. And it has as many elements as these two vectors, except the first element in this product is the first element of always masked times the first element of population size. So that's the first element of this product vector. This is not stored. It just happens in memory. We could store it by assigning, we could make a new variable in it, assign it this, but we don't need to. So that's what is happening with this product, this multiplication here. And then I'm going to go back to the code. So this is a vector that has as many elements as there are counties in a state because we're grouping by state. But then we sum all of them. So I'm going to go back to the figure over here. And when we sum them, it basically adds up all of the elements and collapses that to a single value. And that's the numerator. And then the denominator is just the sum of the population size by state. So I'm going to go back to the figure. And that's just, it takes all of the information in population size. Sorry, these are pluses here, where I'm adding element 1 to element 2 to element 3, et cetera. And that's going to be one value. Anyways, so, it's a little complicated, but, this idea of, vector algebra and these element-wise operations is super powerful and happens a lot in R coding. Okay, so let's run this code. And I'm not going to go through these analyses, but if you were to compare how we calculated mean in these two different ways, the first way did not take population size into account. It was up here. Oh, sorry, let me. This way did not take population size into account. We just took all the data in the always masked column at face value. Here we took population size into account. When you look at the values, they actually differ slightly, but in an important way that makes this way biased towards underestimating values. Anyways, interesting. I explain why that happens with this code here, but because we're reaching the hour mark, I will go to the final segment, which is I'll just briefly summarize what we did today. So in addition to using some old Tidyverse functions from last time, we used some new ones. We used the slice function to select specific rows in a data table, to select them by their number, as opposed to the filter function, which also selects rows, excuse me, but it selects them by some condition instead. We also used the separate function, which basically took a column that had multiple pieces of information into it, and it split it into several columns that we can access independently. And we did this because by putting state in its own column, we were able to do analyses at the level of state. Again, we use the mutate function, which can modify existing columns, and we use that str remove function to get rid of certain symbols in the data that we didn't want. And str remove is one of many similar functions that are in this string R package. There's also another one I like, which is str replace, which allows you, let's say we wanted to replace those periods with smiley faces or something. It would do that in one command. We used select to, oops, I didn't finish this, to select specific columns in our data. And two of my favorite Tidyverse functions, group by and summarize. Again, we can use the information in a specific column and tell Tidyverse to split the data by the values in that column and run a bunch of independent analyses. Take the mean for each state, not, don't use the entire column, but split that column by state. And lastly, we use the summarize function, usually with group by, to calculate some very simple but informative statistics. And if you look at the cheat sheet and we scroll down here, I believe, yes. So here's this summarize function, here spelled in British English. But as you can see, we only use the mean function. You can actually use various functions within summarize. So for instance, instead of using mean, we could have used max, min. Maybe our data are really skewed and the median is more representative, etc. Okay, that's all for today. I'll stick around and ask questions, and thanks for attending. And with that, I will stop recording. Did that stop recording? I don't even know. No.